For the second talk, it's our pleasure to have Benny Applebaum from Tel Aviv University telling us about cryptographic hardness of constraint satisfaction problems. So go ahead, Benny.
Okay, now you can hear me?
Yeah, but we can also see your left sidebar. There we go.
Okay, good. Right, so let me thank the organizer for inviting me, for having this nice workshop, and unfortunately I couldn't make it, but yes, but let me still try to tell you a little bit about the things that I'm interested in, and kind of in the intersection of this workshop. And I'll try to tell you the story of locally computable crypto, while focusing on the two aspects of the thing of this subject. One is the average phase hardness of CSPs, and the other one is the hardness of learning. And you'll see that these things are closely related. And please feel free to ask questions at any point. So the starting motivation is still crypto. You want to generate pseudorandom bits. So a pseudorandom generator takes a short seed like n random bits and expand it into m bits, right? And you want m to be much larger than n. This is a very basic task in cryptography, and we understand it very well. But we have a twist on this goal, and we want to have it like in a super efficient way. So we're interested in locally computable PRGs, ones in which each output bit depends on a constant number of input bits. Okay, so D is the number of input bits. So for example, in order to compute this bit, you have to look at, say, 3 inputs, read them, and then apply some predicate and generate the ith output. Okay. So this question of locally computable PRGs has been studying for at least 20 years, probably. It was mentioned before that. Explicitly, it was mentioned by Brian Milderson. And when you want a very long output length, like think of m as being polynomially larger than n, then the only known candidates that we have are based on what I typically call random local functions, also known as Goldreich function, honoring Oded Goldreich, who suggested this construction in 2000. So let me present the construction. So the hypothesis during this talk is that these random local functions are PRGs, and let me make it a little bit more accurate. So the conjecture says that for most graphs, okay, so choose a random graph, and I'll explain in a minute the distribution. Distribution is just a natural distribution of graphs. And take a properly chosen predicate Q. And then the conjecture says that this function is a pseudo-random generator. Of course, this is a succinct form of the conjecture because it's parameterized by several things. It's parameterized by the locality, by the predicate, and by the output length. And the way that we typically think about it is m as being our target, right? You want to get, say, I don't know, n squared pseudo-random bits, and d as the resource, right? I mean, we are allowed to use this kind of locality, okay? And I said, so for this conjecture, we think about, we talk about most graphs. So just think about, okay, here are some examples, right? D equals 10. Q can be like, take the XOR over 5 bits and then a majority over the other 5 bits and then XOR them together. We'll talk about this predicate. We'll talk about other predicates also. And let's think that, let's imagine that the output is, say, n squared. Okay. So you can think about all sorts of parameters here. And when I say random graph, I typically think about just choosing to connect each output to a random subset of the inputs. Okay? And in many cases, instead of talking about a bipartite graph, it's convenient to think about it as a hypergraph. Okay, so you can think about each green dot here as a hyperedge. So this is just a D-uniform hypergraph with n nodes and m hyperedges. Good. Some variants of this conjecture. So I'm going to keep this as the main version of the conjecture, but there are two interesting variants. The first one is a stronger variant, So it says it's not only the case that most graphs work, actually every sufficiently good expander should work. And it's not completely clear how good expansion is needed to satisfy this conjecture. But for example, you can think about the following version. So you want every T set of outputs to touch many, many inputs, let's say 0.1 times D times this set of inputs. Okay, so you want this graph to be expanding in this combinatorial sense. And we have all sorts of evidence, we'll talk about them, that if you have this property, then say that you have security against algorithms that runs in time, which is exponential in T, in the parameter of the expansion. Okay, this 0.9D is not, it's not clear whether this is the right number here, but note that it's definitely clear that you must have a non-shrinking sets, right? I mean, so if this set is shrinking, so if it doesn't expand, if you have a set that of size T that touches, say, only T minus 1 numbers, then you can really break this thing just by looking at this subset of outputs and ignore all the other inputs and just applying exhaustive search, say, over this set. So you can see that you can easily break the generator in times exponential in T if you have a shrinking set of size T. So some level of expansion is necessary. So this is a stronger variant of this conjecture in the sense that if you believe in this variant, then it implies the for most graphs variant. And you can also think about a weaker variant, and we'll get to it towards the end of this talk, where you just assume that there is some graph. You don't know how the graph look like, but for some graphs, this thing is this conjecture holds, and for properly chosen predicate. I should also say that this predicate, I mean, we'll talk a lot about this predicate, but intuitively, the longer the output length is, we will have to require more properties from the predicate in order to satisfy this conjecture. Okay, so the predicate should be more robust in a sense in order to support longer output. Good. So this is our main assumption for this talk, and it's been studied for a long time. There's even a survey, slightly outdated, but if you're interested in it, then many of the results I'm going to mention appear there. And one reason to study this assumption is as a test case for the real question that we're interested in. Right? So as cryptographer, we try to understand complexity theoretic cryptographer. We want to try to understand is there crypto in P, or in other words, what makes a standard polynomial time circuit good for crypto? Now this question is very hard to understand for general circuits, but maybe we can start with local functions. And you can see that we can prove all sorts of things for local functions that we don't know how to prove for general cryptographic primitives. Okay. And another reason is that this hypothesis or conjecture has very interesting cryptographic and complexity theoretic applications. The most recent one is this obfuscation that I assume that is going to be mentioned in Ayush's talk later. But I will show you today that there are many other complexity theoretic implications of this kind of conjecture. So I think that it's useful also if you want to have a clean assumption that captures a very strong form of average case hardness of CSP. Good. So some very simple implications of this hypothesis. So let's start by just looking at the CSP perspective. So you can think about this instance as a CSP instance, right? I mean, these are the x's are the formal variables, and basically the y's corresponds to constraints, right? So if you have a graph and an output y, you can think about it as a CSP whose ith constraint says that when you look at this restriction of the variables to the set Si, right, this is say the hyperedge of the ith bit, then if you apply the predicate q, the output should be yi. I think about the yi's as just the bits. These are constants. And once you adopt this view, it's very easy to see that when you look at a string that is sampled by applying the PRG on a uniform assignment, then you get a satisfiable CSP, right? I mean, by definition, you have a solution. But on the other hand, if you look at a random string, then with high probability, the value of this CSP is much smaller than 1, just by counting. In fact, if you think about M as being superlinear in N, as we will think about most of this talk, and think about Q as balanced, and we'll see that this is necessary, right? So the value is going to be roughly half, or half plus some tiny epsilon, small as you want. So the pseudo-randomness assumption says that you cannot distinguish between the red and the green, the ansat and the sat. It also implies that it's very hard to approximate this value, or it gives you a nice distribution about over a gap instance of CSP. So, in other words, if you believe that random local functions are PRGs, then you get a nice and arguably natural distribution over CSPs, which is hard to approximate. It's also hard to satisfy, right? I mean, say, finding a satisfying assumption is like assignment is like finding a certificate for the case that you look at the PRG output. And it's also hard to refute because this will certify that you come from the random distribution, from the uniform distribution. So you have a distribution that gives you a very strong form of hardness. And I want to, to note that this distribution is somewhat different than the standard distribution that we typically talk about when we talk about random CSPs. Like it's very different from, say, random CNFs. Well, not completely different, right? The graph is indeed random, like we use, like the graph that that is induced by choosing a random CNF instance. But the constraints are kind of induced also in a somewhat random way, right? I mean, in particular, we're going to see two types of constraints. Either you see 0, this is one predicate, or a 1, okay? So these are kind of funny constraints that are being sampled as part of the distribution. And as I said, if you look at different variants of this problem, like you can play with all sorts of variants of the distribution over the Ys and the distribution over the graphs. Okay. Good. So let's look at it from a learning perspective. So now I'm going to think about a function that is parameterized by x. So think about x as being a fixed string, and this is kind of part of the description of this function g sub x. And the function basically takes an hyperedge, I1 up to ID, this should be a subscript, and recovers the corresponding bits of the string x and applies this predicate q. Okay. So this is a function that takes basically d log n bits and outputs a single bit. And now you can ask to learn this function. So given n-1 random input-output pairs, your goal is to predict the function on a fresh random input. This is like the PAC learning, the classical PAC learning problem. Okay. Now, by the way, that this function, it's a funny function. It's not, sometimes people, may confuse it with a junta. It's not a junta, right? I mean, the function itself has this x, which is hardwired, and you always look at a small window of bits and then apply some predicate over this window. Okay. So PAC learning tells you that given y1 up to ym-1, please tell me what ym should be. And we know by a classical theorem of Yao that if this thing is pseudo-random, then this thing is also hard to predict. So put differently, if you believe in this conjecture, then you get a distribution over this function whose domain is of size n to the d, so it's a polynomial size domain, which is how to PAC learn given n to the s samples where s is smaller, it's some constant smaller than d. Okay, so you have a bounded number of samples, and we believe that it's how to learn. Okay, does it make sense? So let me go back to this slide. So, this kind of, as a hardness of learning result, this is not completely satisfying because we want to, typically when we want to prove the hardness of learning, we want to say that for arbitrary polynomial number of samples, right? I mean, this is the more natural way of talking about hardness. And indeed, it's easy to get such an implication if you scale up things a little bit. So let's take this locality parameter to be not a constant, but say log n, so slightly super constant. And now you can hope that this thing is pseudo-random even when the number of the outputs is super polynomial. And in fact, if you use this expanded variant of this conjecture, then it supports this kind of this setting of parameters. Okay, so if you have a bipartite graph with m slightly super polynomial number of hyperedges, where each hyperedge is of size log n, then it's still expanding for sets which are not, which are say n to the 1 minus delta. Okay, so if you believe in this conjecture, it means that this thing is still sub-exponentially hard. And now, just by using the previous mapping, we get a distribution over functions, which is how to pattern given any polynomial time, any polynomial number of uniform samples. Again, this is hardness over the uniform distribution. Okay, and in fact, I'll show you easily that this is a very simple function. This is a depth-free AC0 function. So let's see why. Remember, I'm thinking about x1 up to xn as hardwired, and my input is just d pointers, right? I mean, tuple of a d tuple of pointers, each of length log n. So the first step, I'm going to recover the corresponding bits of x. So this is a log n local function. And then I'm going to apply this predicate q over this tuple. So this is again a d local, which is logarithmic log n local function. Now this log n local function can be computed by, say, CNF, polynomial size CNF, and this log n local function can be computed by polynomial time DNF. And now I have depth for circuit, and I use the standard trick of collapsing this DNF over CNF, collapsing one level, and I get a depth-free AC0 circuit. So this gives you a very simple function which seems how to learn. In fact, it's even more interesting because if you believe again in this expansion-based variant, then this is how to learn even given sub-exponential time, as long as you're given, like, say, polynomial number of samples. And if this is true, it tells you that this classical LMN algorithm is tight. Right? So LMN shows us that you can actually learn AC0 functions by learning the heaviest Fourier coefficient. If you have quasi-polynomial time, but also quasi-polynomial number of samples. So this conjecture tells you that you cannot improve this element, namely in the sense that keeping the running time quasi-polynomial while reducing the number of samples to be polynomial. Or if you want to view it in the other way, try to improve LMN and break this conjecture. This is also, you know, a viable version of the assumption, of the direction. Good. Question, I think that I saw something. Okay, in case I'm missing someone who's, I don't know, raising a hand or something, I guess that.
Yeah, we'll interrupt you.
Okay, good. Yeah, because it's hard for me to see both the presentation and your faces, so apologies.
Yeah, for many of us, it's impossible for you to see our faces.
Okay, good. Right, so, you know, so this is from a learning point of view, but you can actually think about it as a simple pseudo-random function, and that's actually was the motivation for looking at this variant when in this work with Pavel Rykov. So just by, you know, rephrasing the previous slide, I can get what cryptographers call a weak pseudo-random function that maps m bits to, say, almost linear number of bits. And it can be computed either by an AC0 circuit of depth 3 or by linear time, in the RAM model, right? Where you're allowed to use like a log n size words. And let me show you how this weak PRF look like. So the key again is this x's. So I'm going to look at this as a key. And whenever someone wants to query the PRF on an input, this input, I'm going to let this input define a graph. Okay, so here, unlike in the learning case, I said that, you know, the output can be a single bit. Here I want to generate many bits. So let me think about each input as describing this graph with n outputs. So this will be the output of the PRF. And then if someone arrives with another input, then there's another graph and there are more EI outputs, and so on and so forth. And the observation is that if all these inputs are indeed random, this is what means to be a weak PRF. You're allowed to evaluate the function over random inputs. Then all these graphs are also random, and that, you know, the concatenated graph is also random, and therefore you have pseudo randomness based on this assumption. Good. So what about non-random inputs? And this is important both for crypto and also for learning. In terms of learning, it will say that you were allowed also to make membership queries. So you can basically do it by slightly changing this mapping from inputs to graphs. So certainly if you keep this mapping naive, just let the input specify the graph, then this thing is not secure when you allow someone to query to choose its own inputs. And the reason is that you can, you know, just ask for one graph and then ask for a very related graph, right? I mean, another graph that has some, say, hyperedges which are the same. And therefore, this thing is not going to be pseudo-random at all, right? If these graphs have repetitions or are highly correlated. So the idea is to kind of have here another mapping that maps the inputs to graphs in a way that makes this attack impossible. So the way to do it, or the way that we did it, is to use this kind of fast low bias generator. So think about it as a seeded low bias generator that expands that expands the seed. Ignore for a second this input. Expands its seed to exponentially long output. Right? And we have such low bias generators. And now, whenever someone specifies an input, it specifies some part of this sequence of low bias bits. So there is some part of this long sequence, and use this part of the sequence to define the graph. And what you can show is that the resulting graph is almost expanding by using probabilistic arguments. And this almost expansion can be fixed just by applying a randomness extractor on top of the output. So this is the construction that we had there. And you know, we were happy about it. We were able to show that if you use the expander variant of the assumption, then you get a strong PRF from n bits to almost n bits. It can be either computed by a constant depth circuit over and/or in majority gates, right? I mean, the construction is more complicated because you need these strong low bias generators, and we use algebraic constructions that, for example, do inversion over finite fields, or computed by quasi-linear Boolean circuit. And it seems that you can get sub-exponential security as long as you make Polyang queries. And by the way, an interesting question is to try and show that maybe you get security even beyond it. Okay, we don't know. So, as I said, we were happy about this construction, and we were in particular happy because we could reduce it even to a one-wayness assumption. I'll talk about it later in the slides. But there's actually one very interesting, I don't know if to call it a caveat, but aspect of this construction. So, okay. More low complexity PRFs in Yuval's talk, right? I mean, so stay tuned. So what's the twist in the story? So 2 years ago, maybe 3, it was observed by Oliveira et al. That if you use this construction and use a very efficient expander and a very efficient predicate, you get 2 efficient PRF. So what do I mean by 2 efficient PRF? This PRF actually is breakable. Okay, why? Because the circuit is so simple. Like think about XOR DNF, so things that are related, and we have natural properties that allow you to break this kind of construction. So this is a very interesting result, and basically it tells you that one of 2 things, or 3 things, I guess, should happen. Either, you know, you cannot have super efficient expanders, so you cannot improve them beyond what we have now. And when I talk about efficient, I'm talking about computing the neighborhood function of the expander. Or the natural properties that we have, again, this kind of functions like DNF XORs are tight, you cannot improve them either. Or maybe the conjecture is too broad. So in this conjecture, you talk only about expansion and, you know, appropriate predicate, and you'll have to state somewhere in the conjecture that the computational complexity of the joint computational complexity of the expander and the predicate should not be too small.
Benny, can I ask a question?
Yeah, please.
So highly efficient, can you be more specific?
Yeah, so they have okay, good. So they have several results in the paper. That's why it's a bit vague. So one version talks about NC0 expander. So think about an expander such that if you want to compute the neighbors of so let me just put the picture of the graph, I don't know, whatever. So you want to compute who are the neighbors of this node. So if you can compute it by compute the name of the neighbors of this node by a local function, so a function that depends on a constant number of bits, then this is like kind of too efficient expander. And in fact, the interesting thing is that if you don't care about unbalanced expanders, so you look at the expanders that have the same number of hyperedges and nodes, then there are such constructions. So there is a very nice construction of Viola and Wigderson. So either you can, improve their construction to have to unbalanced expanders, or maybe, or maybe the conjecture is not true, right? I mean, okay. So if you can, sorry, I put it the other way around. So if you can get such a highly efficient expander, for example, then for some predicate that seems to be secure so far, you can actually break this construction. Therefore, falsify this assumption that any expander will do. Okay.
It's not enough that there would be like M would be n+1 because you cannot repeatedly do this.
What?
It's not enough if M is n+1, just one value.
So all these things work with very long. So also their attacks, they actually work in the regime where M is very long. Okay, I don't think that they have anything for the case where M is slightly longer. In fact, for M, which is say n+1, then you can even expansion is not really necessary. Right, you can get things which are just non-shrinking, and by the way, this is easy to achieve by simple manipulation on graphs, and we know that they suffice for pseudo-randomness.
So I meant the result of Avi and so forth. Is that
the result? I assume that they can, they can get. I didn't check it, but I assume that they can get like a slightly superlinear number of hyperedges. But the challenge is to get, a highly unbalanced setting, right? I mean, to get a polynomially larger number of items. Yes. Yeah. So you should read this paper. Unfortunately, I don't have a lot of time to talk about it, but it's really a cool combination of natural properties and expansion and crypto. Good. For me, I should say, for me, the bottom line is that one of the things that made this whole family of constructions so appealing is that unlike standard crypto, we were in a situation where it seems that all you need to talk about is simple combinatorial properties and some algebraic properties of the predicate. I'll get to it within a few slides. And so it could be very appealing to say, forget about computational complexity, give me a sufficiently good expander and a sufficiently nice predicate, and you get a pseudo-random generator. And this result tells you that it's actually not that simple, or maybe not that simple. Okay. Good. Please do ask questions. So let me ask a question. Why should we believe this conjecture? So I'm going to talk about two main potential answers for this question. The first one is that we can prove unconditional security against concrete attacks. And the second one is this reduction to one-wayness that I mentioned in the previous slide. And in order to talk about this first answer, let me ask more concretely, say that you want an output of n to the s for some constant s larger than 1. Which predicates should satisfy the conjecture? Okay, so this is kind of, you can call such predicate S pseudo-random, right? I mean, And when I say satisfy this conjecture, I mean for most graphs. Okay. So the short answer is that you need two main properties. One property is resiliency, and I will define it in a minute. And this resiliency allows you to defeat all sorts of local attacks. And the second thing that we need is some sort of algebraic degree. It will be slightly more complicated than degree, and it will allow you to defeat linear algebraic attacks. Okay, so this is the high-level answer, and let me give you more precise details. So remember, our goal is to say that it's hard to distinguish Y from a random string. So know that this is much more fragile than one-wayness. In particular, each bit here should be unbiased. Right? So it means that the predicate must be balanced. Right? I mean, if this predicate is not balanced, like think about O, like in the case of CNF, then this is bad because you will see a bit which is more likely to be 1 than 0. So you need to use a balanced predicate. So let's look at majority. And I claim that majority, although it's balanced, majority over 3 inputs is actually a bad candidate. And the reason is simple. Let's look at this output and this input, right? I mean, say that this input is 0, then this means that this output is going to be biased towards 0 as well, right? Because this is a majority. But it also means that this output, which also touches this input, is going to be biased towards 0. So we see correlation between two outputs, and this is enough to break the pseudo-randomness. Right? So if you see 0 here, you're more likely to see 0 here than just 1. So you don't want the predicate to be just balanced. You want to be balanced even after fixing, say, a single input. And by the way, such configuration, right, are inevitable when the graph is when you have enough outputs, right? You cannot just avoid these kind of things. Right? You're going to see two outputs that touch the same input. And actually, the more outputs that you have, you'll see more stronger collisions between two outputs. So what you really want is k-resilience. Right? The predicate must be balanced even after fixing k inputs. Or if you want to talk about it, in Fourier language, if you look at the Fourier coefficients of the predicate, then all coefficients of weight less than k should be 0. Good. So this is, by the way, know that this notion of resiliency is somewhat slightly different than what you usually work with when you prove like SOS lower bounds and so on. There you typically say it suffices to have a predicate that supports a distribution which is k-resilient, right? I mean, here you really need the predicate to be k-resilient, and this is because you really need a stronger property. You need pseudo-randomness. So I said earlier that resiliency defeats local attacks, and this observation goes back to this work of Moses, Shpilka, and Trevisan. And later it was extended and strengthened in many ways. So basically, if your output is of length n to the s, then you need the resiliency of roughly 2 times s. Okay, and you can prove that this is necessary and sufficient for against many attacks. So sub-exponential size AC0 circuits, semi-definite programs, sum of squares attacks, statistical algorithm, and so on. And let me give you the idea of the proof. Let's say for this result. So for this result, we use this wonderful theorem of Braverman that shows you that k-wise independence suffices to full AC0 circuits. So let me show you that if you have resiliency and expansion, then you get k-wise independence. So let's fix the set of outputs. And imagine that I already showed you that the first output here is uniform, and also the second uniform and third uniform condition on the previous ones. Okay, let's just look at the last one. So let me condition on some fixing of these outputs. So this means that I kind of condition on some fixing of the inputs that touch these outputs. Now, if the graph is expanding, then this last node here has still neighbors outside this set. Right? And since we have resiliency, and if we didn't fix enough inputs of this output, then this thing is still uniform, right? I mean, the uniformity here is induced by the randomness that is left in this set. Okay. Good. So you can prove that this thing is k-wise independent. By the way, here's a cute question. Try to order these attacks. right? I mean, each of these attacks, is proved in a long paper by spending a lot of efforts. Can you kind of prove a meta theorem that says that, if you defeat, say, AC0 circuits, then you get SOS lower bound for free? This for this kind of problems. Okay, so I'm not aware of simple, I don't know how to call it, transfer theorems for these kind of things. And I'm not talking about the most general transfer theorem, maybe just for CSPs or for this kind of problems.
So Benny, don't they all follow from K-wise independence? I mean,
I don't know how to prove it. That was my intuition. Thank you, Andre. Yes, exactly. I think that should be the right answer, but I don't know how to prove it. Maybe it's easy and I'm just missing something. But for a while, I tried to kind of, maybe the SOS people can answer. I tried to, before this result was out, I tried to establish a SOS lower bound just based on K-wise independent. I wasn't able to do it. So intuitively, I think that the answer is yes, but maybe it's, I don't know, maybe it's an exercise. I don't know how to do it.
So Benny,
Yes.
just to get the question you asked a bit more carefully, is the question that you want to prove that if a predicate is K-wise uniform or let's say K-resilient, then you want to prove a SOS lower bound for every expander? Is that like the question you have in mind?
Yeah, yes. So no, I mean, that's one version of the question. By the way, I didn't say, but for the first item, for example, we were able to prove it for every expander, right? I mean, as long as it's not about random graphs, every expander should imply this thing. But I'm kind of asking about, I would say maybe a meta theorem that tells you either that, if you get security against one algorithm, then you get against the other, or maybe some property that tells you, if you have a clean sufficient condition that allows you to get, all these hardness results in one shot. I mean, of course, you have it, right? I mean, this is the title, resiliency suffices for all these things, but can you kind of do it without repeating all these different proofs? Can you do it directly? I mean, that's the kind of, I mean, okay, it's a semi-formal, it's not a formal question, but I think that it can be formalized in a meaningful way.
Okay, yeah.
Who was asking, by the way?
Sorry, what?
I didn't see who's asking. Please say your name because I can't.
I'm Pravesh.
Good. Hi, Pravesh. Yeah. Other questions? Okay, good. So let's talk about linear algebra. So, XOR is the ultimate resilient predicate, right? I mean, XOR gives you the highest resiliency that is possible, but clearly you cannot use XOR because then you will see linear correlations between the outputs. In fact, if your output is of length n to the s, then you must have an algebraic degree of s, right? Because otherwise you could kind of define auxiliary variables for each possible monomials and then apply this linearization attack. Right, I mean, find the linear correlations. So here's a simple way to keep the resiliency high and increase the degree. Just XOR it with an end of other variables. So n gives you a monomial. So now it's a high degree. And for a while we thought that this is enough. So here's the conjecture. It was even made explicit by Feldman et al. for CSPs. High resiliency plus high degree implies pseudo-randomness or hardness of any form. And well, it's somewhat true in the sense that if your output length is slightly superlinear and you talk about linear distinguishers, then we were able to show that this is indeed true. This is in this work with Andre and Alon that I mentioned before. That is, we can show that this is a small bias generator. However, for larger values of output length, this is not true. So let me tell you about this kind of attacks.
And this doesn't depend on the predicate? Like it's a end of the 5/4 no matter what the predicate is, and
if the predicate, yes. So give me a predicate which has enough resiliency and enough degree, and there, basically degree 2 and resiliency, I think 2 are enough. So for example, take, I think there, for there, it's probably enough to take XOR of 3 bits and the end of 2 bits.
Sure.
Right, I mean, this is the minimal predicate, then you will get a pseudo-randomness here for any expander. And the theorem actually talks just, just in terms of resiliency and degree. And again, I should say that this kind of extend this wonderful paper, the MST paper, in a sense. It adapts the approach from that paper to a more general setting.
Okay, but the
Good.
constant the constant 5/4 doesn't depend on I mean, once you have resiliency and degree, 5/4, this is fixed no matter how high the resiliency and the degree are.
I mean, okay. Let's wait for the next
Oh, yeah,
slide.
sorry, yeah, sorry.
Okay, yeah. Let me just say, the intuition for this kind of theorem, I can tell you, I'm not going to show the proof, but the intuition is fairly simple. So if you look at, and again, it goes back to the MST paper, take a look at the linear distinguisher. Okay, so this linear distinguisher just looks at XOR of some of these bits. And if it looks at XOR of small number of bits, then you're covered by the resiliency because this is below the K-wise independence regime. And if you have many output bits, then this nonlinearity basically acts like a noise. Okay, so you add many nonlinear terms, you can extract enough independent nonlinear terms and then analyze it like you add many biased coins. And when you add enough biased coins, this thing behaves like an almost unbiased coin, right? I mean, like so. So that's the intuition. And indeed, proving this statement from, say, noisy XOR is almost trivial, right? That's always a good simplified version of all these assumptions. Just use XORs and add the noise, say, with probability 1/4 or something like this. Okay, so I told you that resiliency and algebraic degree are not enough, and let me explain why. So let's look at this predicate. And the point is that this end indeed increase the degree, but in a very fragile way, right? This is a single monomial. If this input is 0, then the whole monomial vanish and you end up with a low degree predicate. So it turns out that you can exploit this property, and if you have enough outputs, you can identify a small set of inputs and condition on the event that this small set of inputs is 0, and then get cancellation of many outputs and see a linear dependency. And in fact, you can turn this intuition into a linear distinguisher. Okay, this idea. So the natural, so in order to defeat this attack, you need basically a very natural property, which is bit fixing degree. So the algebraic degree should be at least B, even after you fixed many of the inputs, say B of the inputs. And the theorem that we proved there with Shachar Lovet is that if your output length is n to the s, and you have, say, s bit fixing degree, then this is necessary and sufficient against linear distinguishers. So give me such a predicate. For most graph, the thing will be a low biased generator. Okay. And I can come up with a predicate that doesn't satisfy s bit fixing degree. And for this, for most graphs, or any predicate that does not satisfy this property, for most graphs, you will be able to break it.
Sorry, Benny, just to make sure I understand. So you're fixing B bits globally. And now what's the property that you would like?
No. So for the predicate, look at this predicate. I want the property such that, so let me just present the better predicate. So think about XOR and majority. Even if you fix, say in this picture, think about, right? I mean, unless, okay, majority over 3 is less interesting, but the property says that as long as you didn't fix, you fix less than B bits, the degree cannot drop below B.
This is for a single.
Okay, so
this is for a single predicate, not globally.
This is for a single predicate. Yes.
Okay.
Yes. The
Okay,
attack
thanks.
is what I said previously is how the attack works. Yes. Good. So you want something less fragile than n, then use the majority here. This gives you a better candidate. Now I should say that this is not the end of the story. This is not the end of the story because it turns out that you need a stronger form of rational degree in order to defeat another family of algebraic attacks. So I'm not going to talk about it too much, but let me just mention it briefly. So what does it mean that the rational degree is high? So it's small if an equation of the form qx equals 0 or 1 implies a low degree equation. So think, for example, imagine the predicate that takes an OR over XOR. So you have an OR over XOR. Let's say that all the XORs have evenarity. So say that I tell you that the OR of the XORs is 0. You can immediately conclude, right, that a linear equation, right? You can immediately conclude that the XORs themselves are 0. Okay. So from this description, it's not clear why this is the rational degree, but the reason that we call it rational degree is that there is an equivalent formulation of this condition that says that you cannot write your predicate as the ratio of two low degree polynomials. And what do I mean by algebraic attacks? I'm not going to define it, but basically algebraic attacks allows you to look at these equations and kind of derive more and more and more equations over the output. And the way that we capture it is by using this proof system, the polynomial calculus proof system that was introduced by Clay Edmondson and Paliazzi. So we can show, again, without defining exactly what this thing is, what we can show is that if you have a low rational degree, then you can actually attack this kind of construction. And this attack is actually a refutation, okay? So you can refute a random string. You can show that it's not in the image of the PRG by using this framework. And if it has sufficiently high rational degree, then you can prove that, and based on their works, that as long as the graph is expanding, no such a certificate exists. Okay. So, right. Okay, I'm not going to talk more about this thing unless you're really interested. I can say a few words later. But know that again, this is kind of a cool use of proof complexity tools in order to prove some hardness of attacks in crypto. Good. So how much time do I have?
You have about 10 minutes.
10 minutes. Excellent. So let me tell you about this this transformation from one-wayness to unpredictability. So you could phrase a weaker conjecture or seemingly weaker conjecture that tells that this random local function is one way. Namely, that given the output, you cannot find the inputs. Right? You cannot find an input that corresponds to the output. And again, for predicate Q and the random graph with M outputs. And what we can show, and I'll show you the proof in a high level in the next slides, we can show that under this one-wayness conjecture, the same function is actually somewhat unpredictable. So if you read the prefix, the n-1 prefix, it's somewhat hard to predict the last output. This 0.99 is actually a constant that depends on the predicate or the locality. So think about it as maybe 1 minus 2 to the minus d in the worst case, but some constant. And note that this is exactly the same function. So this is really cool, and this is kind of not very common that you can kind of reduce one-wayness, reduce pseudo-randomness to one-wayness, or some sort of pseudo-randomness to one-wayness for the same instance. And there's another implication that we can show, and we can show that actually this function is epsilon pseudo-random, again for the same predicate, but here we lose something in the output length. So if you want to get pseudo-randomness for some parameter, you have to assume one-wayness for a longer output length. Okay, so there is some loss. Okay. And the cool thing is that, you know, I'll show you. Eventually, I can construct local PRGs from these things. But the cool thing is that it really tells you something about the distribution in which we're interested, right? I mean, it tells you, it supports the PRG distribution in the sense that if you believe that one awareness holds for this predicate Q and a random graph, then you get that some sort of pseudo-randomness. Hold just a second, Rocco. For the same predicate and still a random graph. Okay. Yes, please.
Hi, Benny. Just a quick question. Could you state the one-way function conjecture in a little more detail? F is this mapping from n bits to m bits again, and it's just the conjecture that that's a one-way function?
Yes. So it's n to m, exactly the same distribution. You sample the graph at random, you have this predicate Q, and you assume that this is how to invert. I mean, you can make it more quantified by talking about the, you know, the exact running time of the inverter, but you know.
Okay, thanks.
And by the way, this is the original conjecture of Goldreich, and this was originally stated for m equals n. And in the original paper, he also talks about the expansion. So he talks about for every expansion, this thing is believed to be one way. Okay. And the hardness parameter, I guess, is the level of expansion, right? I mean, he conjectured that any inverter that runs in time exponential in the size of the set that is expanding cannot invert the function. Good. So this supports the PRG conjecture, and you know, all these implications hold for random graphs, but actually there is an extension to expanders. So if you assume one awareness over all expanders, then you get pseudo-randomness over all expanders. Another question, or is your hand still?
Sorry, I'll figure out how to put it down. Ignore it.
Okay, no worries. No worries. Okay. Good. Before showing the proof, let me go back to the CSP perspective. So it tells you that there is a reduction from search to decision, right? And solving the gap problem implies that you can find the satisfying design, which is cool. And it preserves the distribution, right? I mean, we have many kind of, you know, many reductions of this sort, but typically they don't preserve the distribution, and this result preserves the distribution, which is, I think, an important feature. If you want to be a learner now, then this is actually a proper to improper reduction. So it tells you that if you can predict the target function by some arbitrary hypothesis, this is what's known as improper learning, then you can actually recover X. So you can recover the description of the target function. So this means that you can properly learn the function. And again, this is very interesting because typically for proper learning, we can hope to get that MP hardness kind of results. Improper is a regime where we don't expect it to happen. So there's a big step between these two things, and again, it preserves the distribution. So let me tell you the high-level idea of this proof. Let me make the simplifying assumption that the predicate is of the form x1 XOR with some predicate over the other inputs. Okay, so it's very sensitive with respect to the first input. So our goal is to take a predictor, someone who can predict the final output and get an inverter. So how does a predictor look like? Well, a predictor reads this prefix, gets the name of the last hyperedge, and then guesses what should be the output of the last bit, right? It guesses B, and let's say that it's correct with probability half plus delta. So the idea is to run this predictor on a modified graph G prime. So I'm going to take one of these edges, and I'm going to swap it with a random location. I'm going to change it, and then I'm going to run my predictor. This is still a random graph. So I get this guess for the output, you know, which is correct with probability half plus delta. And now that if this guess is correct, then I can see that B equals to YM if and only if these two bits are equal. Of course, the predictor may make an error, and therefore we get what we get essentially is a noisy Toulin equation of this form. And now, once we have a noisy Toulin equations, we can try to collect many of them, and they are all and do some error correction. And there are all sorts of subtleties because this noise, if you do it naively, if you collect all these equations naively, then this noise may be correlated, but you can use re-randomization in order to kind of kill some of the independence and make the proof go through. Basically, you're going to randomize the graph by renaming the inputs or by permuting the inputs, the input nodes of the graph. I'm not going to give more details, but that's the high-level idea. Good. Some crypto implications I cannot resist. If you assume one awareness with, say, a linear number of outputs, then you can get a linear stretch local PRG. So you can get an arbitrary linear stretch by using all sorts of standard reductions. And if you assume a super polynomial output length in the one awareness, then you get also a polystretch local PRG. And actually, this kind of requires some effort because what you get from the previous theorem is something which is kind of a weak PRG. The distinguishing advantage is not negligible, it's inverse polynomial. And you need some sort of extractors to make it pseudo-random, but the extractor should be local as well. And in order to come up with local extractors, you need a construction of highly unbalanced expanders. And this construction, we don't have explicit constructions, but in this paper, we show that you can actually sample highly unbalanced expanders with small error probability and use them as extractors in order to get this result. Okay, so this is with Liran Kahlon, my student. Some drawbacks. So you have a polynomial security loss. You get a collection of local primitives, right? I mean, this is parameterized by the graphs, and you have to assume hardness for most graphs or most expanders. Okay, you cannot start with the hardness of some concrete single graph. So this brings me to the last topic, and I will conclude after that. The question is, can you move from one awareness to PRGs locally and generically for an arbitrary graph? So give me a fixed graph, can you do this thing, this transformation? So the answer is kind of, or sort of. So here's a theorem that we can prove, and basically the idea is to exploit exponential hardness. So if you have a regular local one-way function, so regular means that each output here, say you have a red output and a green output, they have the same set of the set of preimages is of the same size. Okay, so this is the regular mapping. So if you have a regular local one-way function with exponential hardness, then you get a local exponentially strong PRG with linear stretch. In fact, you can slightly relax this regularity condition. So what you really need is alpha almost regular. So this set can be larger, but I have to control the largeness of this set. So it can be larger than the set B by an exponential factor, but this alpha should depend on the hardness that I use. So you need more hardness than blow up. So this is what we can prove. And this kind of assumption is satisfied by Goldreich original conjecture, and also it can be based, therefore it can be based on a single function, and it gives a single PRG that satisfies this conjecture. Let me skip this item. The interesting thing is that this proof actually extends also to the worst case setting in some sense. So what we can prove, the analog theorem to this theorem, is that if you have smooth CNFs, I will explain what smooth is, which are exponentially hard to satisfy, then you can show the free CNF are exponentially hard to approximate. Okay, so the latter implication is known as the gap ETH conjecture. We assume that the gap version of is still hard for exponential time algorithms. And this is what we call some sort of smooth ETH. This is a search problem. Right? I mean, this is smooth CNFs which are satisfiable, and we assume that it's exponentially hard to satisfy them. So what does smooth mean? So this is the analog of regularity. So look at the set of satisfying assignments. This is the green set, and look at the set of almost satisfying assignments, and there's a parameter here that tells you how almost this is satisfying assignment. Right? So they say that they violate some delta fraction of the constraints. Then this set should not be too large, right? So A can be at most exponentially larger than S, and this exponent again should also appear in the hardness level of the CNFs. Okay, so this is kind of a weird structural property. So I'm interested in CNF which are satisfiable, and they don't have too many almost satisfiable assignments. Now, is it plausible or not? So I should say that typical instances that are believed to be hard are actually smooth. So you can show that if you have a local one-way function, an arbitrary local one-way function, or just look at the random CNF distribution, the standard one, saying next to the near the threshold, the satisfiability threshold, then this give you like smooth instances which are believed to be hard, and therefore they imply the gap ETH problem. However, it will be very interesting to understand more generally how this smoothness condition relates to hardness. Right? I mean, it's not clear to me. This is kind of a new structural properties or I don't know, statistical properties of the solution sets of CSP. How much time do we have?
Minus 2 minutes.
Minus?
Yeah, -2.
Okay. Negative. Okay, so let me skip this thing and just conclude. Many open problems, pseudo-randomness against low-degree polynomials, smoothness versus hardness. I actually mentioned it. Here's a cool question. Can you show that if the function is a one-way, an exponential one-way and local, it must be somewhat regular? There are some evidence that shows that this may be the case, and this should be, I think, approachable. How much expansion is needed for security? We saw that if you assume two aggressive relations, then there are all sorts of strange implications. Other implications of the PRG conjecture, like we have a public key encryption that I believe that cannot be broken by SDK, by the way, Andre, or at least we don't know how to break it. You can get hardness of learning log and juntas. Inapproximability of some densest sub-hypergraph problems, you can get it as well. So, and I'm pretty sure that you can get more and more implications from this assumption. Let me end up with a hope. I mean, we need a theory for average case hardness over natural distributions for combinatorial problems. We already have some unconditional hardness against concrete attacks. In this talk, you saw some of them, and many of you work on related things. I think that it will be great to have a more structural theory. Can we have some sort of algorithmic hierarchy, or maybe, and ideally, we'd like to see a distribution preserving reductions, like say theorems that say that if random sat is hard to satisfy in the average case over the uniform distribution, then planted clique is also hard. But this would be a wonderful result to prove. I think that local crypto provides some partial results around these lines, and I urge you to kind of use this hypothesis as a convenient starting point for average case hardness. I think that this is a very convenient test case. So thank you, and sorry for running out of time.
Okay, so thanks, Benny, for the excellent and thought-provoking talk. I guess since we are a little bit late and we had a bunch of questions during the talk, maybe we can have Benny stay online for a little while and take questions after the talk offline. And then we'll see you all back here for the afternoon session too. So thank you.